Well, I didn't have to go very far to find a scenic spot to introduce this lesson. This blossoming apple tree is about 10 feet from my shop door. Lessons 1 and 2 can be considered appetizers. Appetizers for the main event, the main course. Segmented ring construction, probably the most common method of constructing segmented turnings. I've broken this lesson down into 3 parts: how to cut segments, how to sand them in order to achieve better looking joints, and how to assemble them, different gluing techniques, clamping techniques. So let's head back to the shop and we'll jump into the world of mitered segments. I've gone from the apple tree to the apple, just to show you how simple segments can be. This is a cute little device that cuts perfect 8-segment rings from these apple slices. 22.5 degree angles on each side of each segment. But you know, rather than play with apples, I'd rather have a piece of my wife's delicious apple pie. Now, if you're real hungry, a 1/8 piece of this, a 45 degree slice, a piece with 22.5 degree angles, boy, that fits the bill. Or perhaps you prefer lemon meringue. Terry makes a mean lemon meringue pie. But you know, it doesn't matter whether you're dealing with maple or walnut or apple pie or lemon meringue pie. If you cut a piece with 22.5 degree angles, a 45 degree slice or segment, it's still going to be 1/8 of the circle. Well, I guess I could cut up some more fruit or maybe a few pieces of chocolate cake, but I think you get the general idea. Segments can be little guys like this one. They can be bigger. It doesn't matter. They just have to form 360 degrees. I cut most of my segments using a chop saw. Now, I'll show you that technique first. I'll also show how I would go about using a table saw if that were my favorite technique. Before I go to the chop saw, though, I want to explain some terminology. Every segment has a length, the distance from angle to angle. It has a height, which is the thickness of the board from which it were cut, and it has a width, the width of the board from which it were cut. And every segment has 2 miter angles. A common mistake is to mix up the term width with length. Because length is a horizontal distance, people naturally think of it as the width. But width is the width of the board from which it came. I cut most of my segments on this 12-inch sliding compound miter saw. It has a depth stop which comes in handy. It has a slider, although I keep the slider locked most of the time. It has a gauge for the miter angle, and it has a gauge for the blade angle. I also have my saw hooked up to a dust collection system, which is real important if you cut a lot of segments. To improve the saw's performance, I'm going to create a cutting tray. A couple of pieces of MDF, one about 6 inches wide, another about 2.5 inches. I'll put a bevel on one edge so that when I glue them together at a right angle, I'll have a little bit of a dust trap. A bead of glue and some clamps puts these two together, creating a tray which will provide a zero tolerance support for any wood that I cut. A couple of bar clamps secures the tray and allows me to reposition it whenever I need a new curve. My depth stop prevents me from going more than about 1/4 inch into the MDF. I'm next going to check to see if my saw blade is at a perfect 90 degrees to my tray. This type of a cut will easily tell me that. By flipping one end, if it's still a perfect fit, I know I'm exactly at 90 degrees. To keep my material secure against my back fence, I'm going to install a cam. This will hold a wedge that can be quickly moved in and out, which will secure my material to the back fence as I cut segments. Before we can cut any segments, we've got to make a few calculations. What angle to cut segments at and what length to cut segments at. As you may have suspected, there's a tiny bit of math involved. It's not difficult math. It's simple arithmetic. There's no trigonometry. There's no calculus. Nothing to be concerned about. but it does require an understanding of a relationship between a circumference and a diameter. This ring here in my hands, it has a circumference, a distance around its outside, and it has a diameter, the longest distance from side to side. There is a number called pi 3.14 that comes into play here. Every diameter times pi will give you the circumference of that ring. In this case, 15 times 3.14 gives us 47.1. Now let's think of this circle as a ring of segments. Now to produce a ring 15 inches in diameter, we need to know how long to cut each segment. It's a simple matter of dividing the circumference by the number of segments in the ring. In this case, 47.1 divided by 16 gives us 2.94 inches. This is where a handheld calculator comes in mighty handy. In addition to pi, remember the number 360, the number of degrees in every circle. Calculating the required miter angle on each side of each segment is a simple matter of just dividing 360 by, in this case, 32, twice the number of segments, because each segment has 2 angles. To help you understand this a little better, I've created a cutting list. It has ring numbers, ring diameters, number of segments per ring, and so forth. Here I'm filling out the ring circumferences. These numbers are a result of simply multiplying the diameters times pi 3.14. To determine the length of the segments, again, it's just a matter of dividing the circumference by the number of segments which are in each ring. But one more time, segment angle equals 360 divided by twice the number of segments. And segment length equals circumference divided by the number of segments. It is critically important that you understand the relationships between diameter, circumference, pi 3.14, and 360 degrees. To make sure you understand that, let me run through a typical segmented wood turning problem. Suppose you want to make a ring of 2-inch long happy face segments, and you want your ring to be approximately 12 inches in diameter. There's 2 questions. How many segments do you need, and what angle do they need to be cut at? Well, we know diameter times pi equals circumference, so 12 times 3.14 equals 37.68. So if circumference divided by number of segments equals the length, the inverse is also true. Circumference divided by the length equals the number of segments. By doing the simple arithmetic, we know we need 18 segments. And 18 times 2 is 36, divided into 360 gives us 10 degrees per side. Some people might question my methodology. There is a difference between a chord length and an arc length. Don't worry about it. For our purposes, simply dividing number of segments into circumference is more than accurate enough. Well, I think it's finally time to cut some segments. I've set my miter angle at 11.25 degrees, or at least as near as I can guess. And I'm going to cut a series of MDF segments in order to confirm my setting. I'm forming a half ring with 8 segments against a straight edge. This will tell me if my blade miter angle is correct. In this case, I got lucky. Had there been a little gap there, I would go back, tap my miter just slightly, try it again until they're dead on. Now I can cut some real segments. I'm ripping a piece of walnut, and then I'm cross-cutting it on the bandsaw, and you'll see why in a second. To save time and work, I'm going to cut segments 2 at a time. The first step is to trim off those bandsaw cuts, so I've got a fresh miter cut on the ends. Now it's a matter of putting a pencil mark at 1 inch, lining that pencil mark up on the side of my kerf, locking down the stop block nice and secure, making sure I bottom out the tip on every cut, making a test cut, taking that test piece and confirming once again that I've got the right distance, the right length. Is it at 1 inch? Close enough. Once everything is set up, it doesn't take very long to cut 16 segments. A cut followed by a flip of the material, another cut. Before you know it, you've got 16. You got to clean them up. There'll always be a little bit of fuzziness on the edges. If you've done a real good job, these segments will just march themselves into a very nice ring all by themselves. There's one more check that's definitely worth taking the time to do. A rubber band around the 16 segments, tapping them into perfect position, and then holding them up against a very bright light bulb. That will show any defect that may be present. Once I've really confirmed that that saw is set up right, I want to mark it with tape so I can come back to that spot at a later time if I want. So that's worth doing, a little trick. Just slit the tape and just line up the edges when you need to go back to that 11¼ degrees. As I said at the beginning of this section, the chop saw is my favored technique for cutting segments. Before we move over to the table saw, let me give you a few more tips and things to be aware of when working around a chop saw. It's probably obvious, but things have to be kept clean. The dust trap even has to be cleaned out occasionally. A sharp blade is incredibly important, and you've got to use a lot of light. You got to see what you're doing. If I'm making a lot of repetitive cuts, an extra clamp prevents any slippage. If your saw does not have a depth stop, then it's easy enough to install one. Just take a couple of pieces of wood, create a T, a piece of double-sided tape, find a spot where it can be placed in under the the saw mechanism. Keep it out of the path of the saw blade, obviously, and you've got yourself a depth stop. Hundreds of cuts will produce a lot of dust. In addition to dust collection, I have a fan going right through the wall behind my saw. Another important consideration, think about the height of the saw. If you're making hundreds of cuts, it's hard on your back if you've got to stoop over. I've placed my saw quite high, as you can see. I never have any back problems. My arms get tired occasionally, but it sure is easier on the back. A table saw is a wonderful tool, especially for ripping boards. But for cross-cutting, it has serious limitations. Those limitations, however, can be overcome. A little bit of material and time, you build a sled similar to this, and you'll be able to cut very accurate segments. I built this sled with a couple of hardwood runners that, slide in the slots smoothly but snugly. That stack of blue painted MDF at the front of the sled is just for stability. The green board is 3/4 inch MDF, an elevated platform for the material being cut so that the cutoffs will exit onto a exit ramp. The yellow board is a miter gauge that's been locked in place at 11¼ degrees. And this clamped on stop attached to the fence is easily adjustable by just making adjustments to the fence. Just as I showed with the chop saw, I'm making a pencil mark. I'm lining the pencil mark up on the side of the kerf. I'm adjusting the stop, making a test cut, and then measuring that test cut before I proceed. Then I'll cut 8 pieces, line those up against a straight edge, and check those for accuracy. I'm using this piece of MDF that I've doodled on to illustrate 2 different ways to cut segments. First, you can cut, flip, and you'll get identical segments. This second method produces segments with a more consistent grain look, but it does waste wood in between the segments. I'll cut some segments and show the difference. Here are 2 small boards of kingwood. As you can see, the grain is very similar. I'm going to cut one of these one way and cut the other a different way. First, I'll make a black line down one side so I can keep my orientation straight. Trim off an end, cut a segment. And after that segment's cut, I'll take a minimum amount of wood off so that I can cut another segment in the same grain alignment as the first. and I'll continue this process until I've cut all my segments. This other stick I'll mark with a red line, and I'll cut these in the more traditional way of just following each cut by a flip, lining it up, making another cut, so forth and so on until I've generated all my segments. Half of these will have the grain going one way, half will go the other way, but there's no waste in this method. So here's the result. One ring, the grain is all aligned the same way. The other ring, the grain is aligned back and forth. I don't like that look so much, so I'm going to mix those up. I'll glue these together and put them on the lathe, turn them so you can see the difference in appearance. Before gluing these segments together, I'd like to spend a little time talking about sanding the end grain of segments before gluing segments together. I've seen a lot of very nice wood turnings done without sanding the segment ends. And I've seen wood turnings with unacceptable dark glue lines. And in every case, those turnings were done without sanding the segment ends. As for myself, back in the early 90s, my friend Ray Allen convinced me that sanding those segment ends was worth the trouble. And ever since, I've been a believer. I'm going to do a little experiment with this stick of holly. I'm going to cross-cut 4 little 1/2-inch long pieces, and I'll sand just the center of the 3 seams. And then we'll do a little examination of these seams. Between 2 and 3 has been sanded. Now, before gluing these, I'm going to put them under a microscope. I'm applying a little graphite from pencil just to show the difference a little more clearly. This is a microscope connected to a computer which has 130 power magnification. The footage is pretty remarkable. The top piece of wood has been lightly sanded with coarse 80 grit sandpaper. The lower piece of wood shows the saw blade surface unsanded. I'm gluing and clamping all 3 seams at the same time just to ensure that the clamping pressure is equal on all 3 joints. And by the way, I didn't use those graphite stained segments in this glue up. Now that the glue is dry, I'll just clean up those surfaces on the disc sander, touch it up with some 220 on the workbench so we can see the surfaces better. There is a difference between these 2 seams. The difference is very subtle, but it's there, and it can be seen. Multiply that all over a vessel, it can make a big difference. To use the words of one of our former presidents, let me make one thing perfectly clear. You do not have to sand all the segment ends in order to produce a good-looking segmented wood turning. However, you may want to consider doing so because the advantages of using a sanding jig on your segments are numerous. By using a jig, you'll improve the joinery, but you'll also achieve a more consistent length on all your segments. Sure, a saw will produce consistent lengths and consistent angles, but what do you do if during the assembly of a ring you find one segment that's maybe got a burnt mark or a deep score mark from a blade? You know, anything like that can happen. So what do you do then? Well, you sand it off and you improve that joint, but by doing so, you've altered that one segment, and by doing that, you've altered the roundness of your ring, and keeping rings round is very important. Keeping rings round is extremely important, and I'll cover that in more detail later on. So, having made my little speech on the benefits of a sanding jig, let's go in the shop. I'll walk you through the steps of building a sanding jig for a 12-inch disc sander. I just acquired this 12-inch disc sander. I've been sanding my segments on my 20-inch for quite some time now, but I didn't think it'd be fair to demonstrate a sanding jig on a 20-inch disc sander since most people don't have one. This sander has some impressive features: a very stout lock for the table angle, a micro adjuster for that angle, a built-in brake, and most impressive, a built-in fan for dust extraction. Most sanding will be done with the sanding table at a right angle. A square will work, but a parallel board, a sanded square, and then a pencil mark applied, and then flip the board over. Lightly touch it and check to see if the pencil disappears evenly. If it doesn't, make an adjustment and do it again. You'll also want to make sure the table slot is parallel. If it's not, make whatever adjustment is necessary until it is. My jig will consist of a strip of hardwood which slides back and forth in the table slot, a piece of 3/4 inch MDF about the same size as the table, and then another piece of hardwood which will be attached to the MDF. This will have a bevel under one edge, creating a dust trap. Next, I'm going to attach the fence to my jig platform with some glue and spring clamps. I'll triple check to make sure that this fence is square to my platform. That's very important. While waiting for that glue to dry, I can start work on other jig components. Next, a stop block with a 22.5-degree angle cut. So here's my stop block, which will slide on the jig platform. I've milled a couple of thin strips of wood and another piece of hardwood, which will act together as a clamp to hold that stop block in position. This will make a lot more sense in another minute. It's important to seal the jig. I want it to slide smoothly, and I don't want it to warp after a little use. It should take 3 or 4 coats of clear lacquer finish. By clamping my top board to the fence, I can drill a pair of holes directly through and then use the exit hole in the underside for a bigger bit. I can then enlarge that hole to accept 3/8 inch diameter bolts, which will be used in the clamp. To lock the bolts in place, I'm using some 5-minute epoxy. Be careful not to get the epoxy on the threads. Drive them in. It should be a snug fit. And while this is curing, I'll go on to the next step. Using a Forstner bit, I'm drilling a series of holes in order to create a pair of slots which will fit over the pair of bolts on the jig. Next, I'm gluing on the thin strips to the underside of my clamping plate. These strips will come in contact with the top of my jig fence as well as the top of the angled stop block. Next, I need to build a couple of clamping knobs, 3-inch diameter circles, dividing the circumference into 8 points, drilling 8 holes around each circumference, and then rounding the edges with a rounding bit on a router. The bandsaw makes quick work of cutting the knobs out, and then the disc sander can be used to round the tips of all the knob handles. A little epoxy secures the nuts in place. The final assembly step is to install the guide rail on the underside of the platform. A piece of double-sided tape comes in really handy. Place it in the slot. Take the platform and put it snugly against the sandpaper before you make any contact with the tape. Press the rail up onto the surface, clamp it in place, secure it with some pressure, drill some pilot holes for the screws, enlarge the hole for the screw shank, and then countersink. 4 number 10 screws secures the rail to the underside, and then a gentle pass with the sander on trims the MDF so you have a nice snug fit. The bandsaw can trim off the rail extensions, and a little wax on the rail completes the job. This baby's ready for a test drive. Here are the other components. Here's the stop block, which can be positioned where you need it. The hold down device slips over the bolts that were epoxied in, and a couple of beveled washers with the locking knobs that were earlier made. Those beveled washers I created by just drilling a hole in a piece of MDF and then giving a thin washer a good wrap with a mallet in order to create a spring. So now that I've got this jig built, you're probably wondering, how does it work? How do you sand those segments to get, consistent angles and consistent lengths? I'll demonstrate. We'll sand some segments, and you'll see how this operates. Here's 16 segments straight from the miter saw. I've clamped down the stop block, so minimal material needs to be sanded. A very light sanding of the first end of the segment. The segment is flipped over. The second time around, I bottom it out right against the fence at that point. The process just continues. You sand one side, flip it, sand the other side, bottom it out on the second side. The retrieval of the pieces is probably the trickiest part of the sanding. A fresh pencil eraser works very well, as does a moist finger. This slick little device is just a sharpened Allen wrench installed in a handle. As you retrieve the pieces, make sure you keep them flat. Don't let them flip around. And obviously keep them away from the upside of the sanding disc. The first time you use the stop block, it's likely to show an inaccuracy. Here's a ring that has a gap to the inside. The angle was off a little bit. We need to adjust it. If when you assemble a test ring, you have a gap to the inside, that means that this dimension right here is too small. So to even things up, that means you have to take a little material off the outside. To take more material off the outside means you have to take a little material off this end of the stop block, which will allow you to take less here and more there. Let me say that one more time. If when you assemble a test ring, you have a gap to the inside, that means that this dimension right here is too small. So to even things up, that means you have to take a little material off the outside. To take more material off the outside means you have to take a little material off this end of the stop block, which will allow you to take less here and more there. It's a trial and error thing. You just have to play with this angle, sanding just smidgens off until you get this angle precise, so that in this case, 16 segments form a perfect ring. It takes very little sanding to adjust that angle. Remember, your effect is being multiplied 32 times. I'm also putting a bevel on the underside just to create a dust trap. That'll make things slide easier. So here's the 16 sanded segments being secured with